Okay, so we saw Fourier transform 2 lectures ago. Yesterday we saw spatial filtering. So the thing is, we have an image. Let's go here. So we have an input image, both through linear filter, and then we have the image that has been filtered. And we saw it with low-pass filters, but usually they can be done with anything. We also saw edge detectors. So we saw low-pass blurring filters. We also saw high-pass. Yesterday we couldn't use the words low-pass or high-pass because we didn't have the concept of Fourier yesterday, but we presented them as edge detectors. High-pass filters. So today and yesterday, what we saw, we focused on how to apply these filters. And we saw a couple of strategies. One was moving average, moving the other one was shift strategy that was shift multiply. Okay, so today what we will see is another way of these two words and these two work in real space. So today we will see to do the same operation but not in Fourier space. And we will call it kernel multiplication. And we will exploit a property of the Fourier space. This property says that if you have a convolution, you do the Fourier transform of this convolution. Then this is the Fourier transform of I multiplied by the Fourier transform of H. We also write it this way. So when we put hats in this context, it is Fourier transform. So the Fourier transform of the result is just the multiplication of the two Fourier transforms. So we will do that today. So let's see how to do that. Okay, so yeah, this is the property I just mentioned. So if you have the Fourier transform of the convolution, it is the multiplication of the two Fourier transforms. And by duality, if you have a multiplication of two functions and you do the Fourier transform, then you have the convolution in Fourier space. So convolution in real is multiplication in Fourier space. And convolution in Fourier space is a multiplication in real space. So this is one of the properties of the Fourier transform. So the thing would be, okay, I want to convolve these two images. So I want to take this image, convolve it with this, so I will compute the two Fourier transforms. I will compute point-wise the product, and then I will do inverse Fourier transform. Yeah, this is how to do that. This is a reminder that these functions here have been represented with the origin here in the middle, but you know that when you do the Fourier transform, you have it in the corners. So you have to do this effective shift operation before. So this effective shift that brings you from this representation to this representation where the origin is in the middle. Yeah, this we already saw. Okay, so now we can apply any filter Fourier space. So let's say that our Fourier transform power let's do it with power spectrum. So the power spectrum density of I as a function of omega. Omega is the module of the vector of the frequency vector. So let's say this is this. Let's put names here. So this is pi. This is minus pi, and we know that this is periodic, period to pi. So we multiply this by the kernel. So multiply by the kernel, and with this one, or this could be a low pass filter, or it could be the one shown in the slide, and it's something like this. So this page in the slide was 1 over omega. So it is a radially symmetric kernel that behaves as 1 over omega. So this is actually distributed if you have to turn it around to dimension. So the feature here is that at high frequency, both of them, they have low values. So the higher the frequency, the lower the value, and the smaller the frequency, the higher the value. So this is the common feature of these two filters, and that is why they are called low pass filters, because the low frequencies can go through the filter. The high frequencies, they are dampened or eliminated by the filter. Okay, so here we have one of them, could be this. And here you see the module of the frequency spectrum. This is omega x squared plus omega y squared. So you can have a sharpening filter. So a sharpening filter could be opposite. The high frequencies, they are boosted. So the high pass filter will look like this. Because of the periodicity, at some point they go down. So they look like this, or they look like this would be one of them. Module of omega, absolute value of omega, or the module of. And then the characteristic here is the opposite. Here it is high, so high frequencies can pass through the filter, while low frequencies they cannot pass. Okay, so now, so here we have, yeah, you can multiply by alpha, so it changes the slope. Yeah, this is again a reminder of this property. So let's see. So let's say that we have this is the filter response, the transfer function of our filter. So it is zero everywhere except the low frequencies that have value 1. So if you do the inverse Fourier transform, that is the point spread function. That is the impulse response of the filter. So you are conforming with this or multiplying by this in Fourier space. And here we are representing the two. So in Fourier space it is red, in real space it is black. And then the filter looks like a sinc function. The actual the action form of that function is called the gene. So when things have radial symmetry, that function is somehow the gene of R. And just a reminder, this sinc of R was something like sine dx divided by dx. And this is something similar, but you have the basic function. It is like this. So this gives somehow this basic function comes from the fact that the things are radially symmetric. Okay, so if it is one thing, it is a sign, but if it is radially symmetric to dimensions, it is this basic function. Okay, so now let's make our filters smaller in Fourier space. So if it is smaller in Fourier space, it has to be wider in the other space. So this is the impulse response. Here we have a profile of the two. It makes sense because if we let only lower frequencies pass, these details have to be on this detail. Has to be a more coarser function, and the larger this one is, the closer, so the more rapid it can vary. So this is a manifestation of, again, of this uncertainty principle that we mentioned a couple of lectures ago. Okay, so let's filter real images. So let's say that we take this image. This image. This is the Fourier transform. So this is the power spectrum density. This is the phase spectrum. Then we put the ideal low pass filter in Fourier space. Then we multiply. So here is the multiplication of the two. And then we do the inverse Fourier transform. And this is what we get. For comparison purposes, we have here the original image. So what we have is just the coarse approximation of this image here. So like this is expected. Yeah, this is another comparison. Okay, so let's do it now with a high pass filter. So a high pass filter is the opposite. So it is 0 at the low frequencies and then 1 at higher frequencies. This is how the impulse response looks like. So we see we have a spike in the middle and then it oscillates. Actually, this one is interesting. What is the average of all these numbers? So this will have a lot of numbers. Here we see a few of them. So what is the average of all these numbers? Has to be 0. Has to be 0 because the 0 frequency, it is the average of your image. So if this is 0, because this is here it is 0, here it is 1. So the average of all these numbers have to be 0. Okay, so now yeah, we have the ideal high pass filter, we multiply, this is what we get. Or we get just the edges. So an edge detector, a high pass filter is another kind of edge detector. Okay, then we can have band pass filters. Or yeah, so how can we get a band pass filter? So I want to get this band pass filter. So one trick to do that would be, okay, you construct a low pass filter, wide support for your space. Another low pass filter with small support for your space, and you subtract the two, and then you have a band pass filter. So let's see that is already more detail here. So let's say that I have my Fourier transform here, and I multiply by a function. This function will be h1 plus h2. So then this is I h1. Let's put coefficients from h1 plus b by h2. So then, for instance, this low pass filter, we have pass filter, so we have h1 like this is 1, 0, this is omega, and we have this is Fourier transform, this is Fourier transform, we have 2, 0, this is omega, this is 1. So, and now we put A equal 1, B equal minus 1. So we will be subtracting this one from this one, and this is what we get. So that means that you can take your image. We have space. So we can take our image. You can go through two filters. One is H1, and one is H2. And then, sorry, this is small h. And then we can add the two. This will be the filter image. And this one has to enter with minus sign. And so this will be our filter bandpass filter image. And these also give us a clue how to do high pass filters. So a high pass filter looks like this. So it looks like this. Image. I will put it here. Final font. So that in the design. So the design looks like that. H1 minus H2. So what is H2? And what is a suitable H1? So this can be H2. So this is H2, it's a function of omega, this is a function of omega, this is omega, and here we have H1. So what if I do like this? This is 1. So if I subtract this one minus this one, then I have a high pass filter. This is no filter. This is letting everything pass. So this is just smaller. So this is take the image, and then you split it. Here you will have H2. On the top you don't have an image. And then you simply add them with the minus 1 here. So this is a high pass filter. So this is a high pass filter altogether. This is a high pass filter. But this one is a low pass filter. And here it is the same. These two are low pass filters. But this one altogether is a band pass filter. Okay, so let's do that. So we subtract these two, and then let's see what happens. So this is the low pass filter with the big radius. This is the low pass filter with the narrow radius, and then we subtract this one from this one. This is the result. So now we have edges of a given size, and the size is given by the frequencies that you let pass. Yeah, all these are different versions of that. Okay, so you may remember that we have this uncertainty principle, in which if something was compactly supported in real space, it was very wide in Fourier space. If it was wide in real space, then it was narrow in real space. We have seen that actually here when we presented the low pass filters, we have seen that effect. So this one here, this was relatively narrow in real space, in Fourier space, and it is wide Fourier. This is even narrower, and this is even wider. So this is this uncertainty principle that we have from the Fourier space. This we already saw and discussed the other day. The problem is that when you have steps in Fourier space, you are convolving with something that has oscillations. This is coming from the C, the D, and so on. So you have all these oscillations. And then if you apply the convolution with the function with an image, then you have all these ripples. So all these ripples, they are kind of nuisance entities. So we don't want the ripples. And then we look for another function that can eliminate the ripples. So instead of filtering with ideal filters, we will filter with Gaussian filters. So the Gaussian filter has a maximum value at the origin, so at zero frequency, and then they decay following the Gaussian. Then when you do the inverse Fourier transform, the inverse Fourier transform is another Gaussian of different sigma. So this is some sigma in Fourier space, this is some sigma in real space. The two sigmas are related. And this is the formula of the Gaussian. And then this is the formula for the two-dimensional Gaussian. I think it's a little bit obfuscated here, but a 2D Gaussian, not always, but the ones we are interested in, they can be factorized. So this is quite wonderful. So let's say that we have a Gaussian. We have a function that is Gaussian of x. We have some sigma. Then we can construct a 2D Gaussian. 2D Gaussian. Will be separable, so you can have sigma x times sigma y. So it is a product of two Gaussians, when you multiply the two, this is the kind of shapes you have. You have this, the same sigma for both, then you have this kind of shapes. Okay, then we convolve with that. When we convolve with that, then there is a smooth transition. That is because of the low-pass filter, but there is no ripples. So that is very nice. Actually, the Gaussian is the function that in a certain principle says somehow this is representing the support in real space. This is somehow representing the support in Fourier space. Then the product of the two is larger than something. So the function that reaches the one, it is the Gaussian. So it is the one that has the minimum product of support product. Okay, then and we can compare with the ideal low-pass filter. So this was the Gaussian low-pass filter. This is with the ideal. So we have removed the fringes. And then we may study a little bit more the low-pass filter, the Gaussian low-pass filter. So we have a Gaussian in Fourier space, we will have a Gaussian in real space. And here we have the two Gaussians representing. And if this Gaussian is bigger in Fourier space, then it will be narrower in real space. It behaves as it should. Okay, then we can filter with this Gaussian. This is the result. This is the filter image. The labels are mistaken. So this is the filter image with a given sigma equal 8. And then we can define Gaussian high-pass filters. And we already know the tree. So the Gaussian high-pass filter is 1 minus the Gaussian. So if we do here, one of the Gaussian, say that this one make it Gaussian, then we have the Gaussian high-pass filter. Okay, so that is what we are doing. So 1 minus a Gaussian has this shape. Then this is the impulse response. The impulse response. Actually, that is interesting to see in with formulas. So let's see this filter again. So this filter is there. So what we are having at this point, we have at point is on one branch we have I minus I convolved with H2. This is the same as I convolved with delta minus H2. So on this branch we have a delta response. On this branch we have minus H2. So this is the impulse response of the whole filter. So delta minus H2. And that is what we see here. So we see a spike minus the Gaussian. Okay, then so this is the high-pass filter. Then this is the multiplication of the two, and this is the filter image. And then we can make much bigger high-pass filter. So this low-pass filter, the one we have subtracted, is much bigger. And then we are letting only the high frequencies to go through. That's why we have a less energy here, because there are fewer, less energy going through the filter. This one, many more frequencies can go through. And we see many more details. will remove or we attenuate most of them, and we don't see so much. Okay, and then we have Gaussian bandpass filters, so that is not required. So you take two Gaussian low pass, subtract the two, and then you have a bandpass. And then this is a low pass with wide area, low pass with a narrow area, and this is the subtraction. This is a filter. This is the impulse response. Again here. And you know the average of all those numbers is against 0. The average of all these numbers have to be 0 because at 0 frequency you have 0. And then another example with different parameters. Then we can compare the ideal and the Gaussian low-pass filters. So we have ideal low-pass filter, ideal high-pass filter, and then we can compare with the Gaussian versions. So you can see here you can see the ripples. You see the ripples. So especially when you compare it to Gaussian, see there are some ripples there. Same for bandpass, and so on. So what about the power spectrum? Okay, so the power spectrum, remind that it is so let's write it here. So we have seen this, but this is a clear reminder that this is good to remind. So let's say that we have an image. Then we can compute the autocorrelation of that image. So the autocorrelation with the lag is the expected value of I of R multiplied by R plus N. This was called the lag. And now we look at the Fourier transform of this one. So the PSE of I, the given frequency is the Fourier transform of the autocorrelation function. And if the image is deterministic, this one is deterministic, okay? And this is this one. So, but only if it is deterministic. Okay, so this is the power spectrum, this is the phase. Phase, and again, a reminder, the phase is the angle of I as a complex number. So for every frequency, you have a complex number, and you can compute the phase of that complex number. Okay, so when we filter, we are another interesting result. This is general for any system, so it is not only for images. So let's say that you have an image that goes to a system. So let's put them in Fourier space. And then you get an output. It's called the output J. So the power spectrum of J is the power spectrum of I. I'm not using arguments. It is understood that it is in frequency space. This thing is only defined in frequency space. Multiplied by this squared. This is the general result of systems. So this is what we are seeing here. So we have an original power spectrum, and then we are multiplying by H squared. Okay, then this is original phase. branches. In one of them, we have a high pass filter. And the other one, we don't do anything. Now, instead of subtracting, we add. So we add J. J, Fourier transform of J would be the Fourier transform of I, 1 plus I pass filter. So that means that J, the shape of this filter here, so the shape of this will be 1 plus something. So this is omega, and this is this one. So it starts at 1, and then it is boosting the high frequencies. This is what the high pass filter does. And we are not losing anything, and then we are boosting the high frequencies. So this is what we have done here. So we have the original and then the sharpen. You see better the sharpen. See? And the reason is that because you may remember from one of the first lectures, our eyes like edges. That is what we see. We only see the edges. So if we boost the edges, we like more this image because we see better edges. So that's it. No question.